The topic that we will discuss in this lecture is simple harmonic motion. First, we will discuss the various types of motion. The common type of motion is translation, which means a particle is moving over a straight path or a linear trajectory. So translation is a linear movement. The second type of motion that we can think of is vibration, which we also called oscillation. Oscillation means to and fro motion or back and forth movement. That is, a particle is tracing a path and retracing it back. So it is a to and fro movement. Or we can say it is a back and forth movement. So, in vibration or oscillation, a particle moves along the same path. Over and over again, that is repeatedly. It repeats its journey from left to right and again from right to left. Another type of motion that we can think of is rotation. And rotation means motion along a circle or along an arc. An arc is a part of a circle, or we can put it in this way: rotation is movement along a curve. And finally, a particle might move from one point to another point using all these types of movement or any two of these movements. So it might be a combined movement. So a particle can vibrate and change its position along a linear path, or it can rotate, and so on and so forth. It can also travel in a helix, which is a combination of rotation and translation. In this class, we will be concerned with vibration or oscillation. The vibration or oscillation. So example of vibration or oscillation: motion of, say, prongs of a tuning fork. Now this is a tuning fork and these are called prongs. So this is one prong and this is another prong. Bob of a pendulum. balance wheel of a watch. The wings of a flying bird. So the wings move up and down, and there is a definite pattern of movement. So it oscillates or vibrates. The lub dub of heart. And this is referred to the beat of heart. So the heart beats. And finally, when we walk, our arms also execute a definite pattern of movement. So arms of a walking person. Let us explore now the cause of oscillation. So what causes a system to oscillate? And the answer is straightforward. There are two reasons. One is the elastic property of a system, and we'll explain it. And the second cause is the inertial property which a system has. So due to these two properties, a system executes oscillation. So let us explain it. Suppose this is the x-axis and this is the equilibrium position. Of a particle, and let us apply a force on it. So apply a force on the particle and take it somewhere else, say here. And this is done against the wish of the particle, as a result of which reaction force develops within the particle. As the system that was sitting pretty in equilibrium position was forced to change its position, and as a result a reaction force develops within the system, and the property due to which the reaction force develops is referred to as elastic property. So the very development of a restoring force within the particle is because of its elastic property. And this restoring force tries to oppose the applied force, and the two are equal. Applied force is equal to the restoring force. So let us write it down. So system, when displaced from equilibrium position, by an applied force, builds within it what is called a restoring force. So we'll write it. This development of restoring force is due to the property of elasticity of the system. It is due to elasticity. And what is the role of this restoring force? The restoring force opposes the applied force. Of course, up to a certain limit. If the applied force is infinite, then of course the system has to yield to it, has to obey what the applied force says. But within elastic limit, the applied force is balanced by the restoring force. The restoring force tries to restore the system. That is, the restoring force tries to bring the system back from its displaced position to the equilibrium position. So the restoring force equals the applied force. Within elastic limit, and this means the applied force should not be too large. And should be within elastic limit. Now, when the applied force, which was equal to the restoring force, is removed or withdrawn, then obviously the restoring force becomes unbalanced. Now, this unbalanced restoring force will restore the particle, that is, take the particle back to its equilibrium position. Again, a particle in motion will continue to be in motion as per Newton's first law of motion. So the system cannot stop at the equilibrium position, but due to this inertial property will be carried on to the other side. So let us write this. When applied force is withdrawn, restoring force becomes unbalanced and takes the system back to equilibrium position. But due to inertia, the system will overshoot. Actually, velocity cannot suddenly become zero at the equilibrium position. So now system moves to the other side. Clearly, as the system is now on this side, again, the tendency of the system would be to be at equilibrium, and therefore again a restoring force will develop within it that will try to restore the system back to the equilibrium position, and the process repeats. So let us write it down. Restoring force will develop again. Trying to bring system back to equilibrium position. The process repeats and system oscillates. System oscillates. So this is, say, the x-axis, and this is the equilibrium position of the system where the system was sitting once upon a time. Due to applied force, the system was displaced, disturbed, and moved away from this point to some other point, say here. And a restoring force has been developed within the system because of the property of elasticity. Actually, the system does not like it to be driven here, and therefore it reacts. And it reacts through development of a restoring force within it. Now there are two things here. One is the amount of displacement, which is, say, x, and the amount of restoring force that is developed within the system. And that restoring force let us call F. Now are they related? That is the point which we will now discuss. So what we'll discuss now is the general dependence of restoring force, that is F, on displacement, that is x. And clearly we will be limited to one-dimensional discussion. It is clear that the more the system is driven away from where it was sitting, the more disturbed it is, and the restoring force developed will therefore be more. So large X means large F. But if it is slightly disturbed, the amount of restoring force that develops within it will be very small. So we expect F to be a function of X. And if X is large, then we expect F to be large. And let us write down the relation between F and X through a polynomial, that is a series in X, polynomial of positive powers in X. So this is important and we'll explain it further. So let us write the polynomial. F is a constant term plus another constant term a1 into x plus a2x square and so on and so forth. So this is the expression of restoring force that we assume in terms of x. The displacement and a0, a1, a2 are constants. And we are writing this as a consequence of the property of elasticity, because development of restoring force in a system is a consequence of elasticity. Now it is clear from here that if X is large, then F is large. So we can indeed write this type of relation. What if we use the negative powers? Can we rewrite this series in terms of negative powers of x? So in other words, is a relation of the type, say f is equal to some constant by x, some another constant by x square, and so on, be possible? So is it possible? We see that as x is large, f becomes smaller. So this means this type of relation is not possible. So it is not possible as it is not consistent with the property of elasticity. Because clearly this is not what property of elasticity predicts. So let us accept this relation, but we have to fine tune it. We have to check whether this form is alright, or we have to make further corrections. Now at equilibrium position, that is when x is 0, obviously the system is not disturbed and the restoring force is 0. There is no applied force, so there is no restoring force. So at equilibrium, when no one is disturbing the system, f is 0. So from this relation what we get is f is 0 into x, which is 0, plus a2 into x square, which is again 0, 0 square, plus etc. And this means a0 is 0. So putting a0 equal to 0 we get. So this is the general dependence of restoring force F on X, the displacement. We note that this dependence of F on X is complicated. This is because the expression contains a linear term x to the power 1. It also contains a quadratic term x square, plus there will be a cubic term and so on. Now this is the linear term. This part is the quadratic term. So it is the linear term because it is proportional to x to the power 1. This is quadratic dependence because it is proportional to x square, and similarly we will have cubic, etc. Let us write another term. It will be a3 x cubed plus and so on. So this is the general dependence, which is extremely complicated. Now this is the cubic term proportional to x to the power 3. It follows therefore that this portion is the non-linear part and this portion is the linear part. So we can write it as the non-linear part. And this is the linear part. We will soon see that if x is small, then this nonlinear part can be neglected and restoring force is proportional to the linear part, and then the motion will be simple harmonic. We therefore now discuss what is simple harmonic motion. We consider system to be slightly displaced from equilibrium position. So, if this is the equilibrium position, this is the x-axis, and the particle has been displaced, and therefore in course of its motion it is somewhere here, say, and the distance from the equilibrium position of its current position is x in time t. Now if it is slightly displaced from the equilibrium position, then x will be small. So this means x is small. And this reminds us of the 4-degree restriction. That is, the angular movement of an oscillator from the equilibrium position should be theta, which is less than or of the order of 4 degree. So it should be a small amplitude oscillation. So if system is displaced by a small amount, then the amplitude is small, x is small, and therefore the oscillation will be called small amplitude oscillation. Now it is clear that if x is small, then x square, x cubed and other higher terms are smaller still, and therefore can be neglected. So we can neglect x square, x cubed and higher terms. In other words, we can neglect the nonlinear part. So this means we can overlook nonlinear part. Nonlinear part can be ignored for small amplitude oscillation. The linear part is only there. So let us write linear part is present only in f, in the expression of f. In other words, f is just a1x. So the motion being linear is of simple nature. And f is just proportional to x. And that is why we say that restoring force is linear. Under small amplitude oscillation. It is x dependent only. Again, it should be noted that the force is restoring in nature. So, wherever the particle be away from equilibrium position, this force always tries to bring the particle back to equilibrium position. So it should be directed not along x but away from x towards the equilibrium position. In other words, F should be negative if the particle occupies a positive position. This means that this A1 should be negative. So A1 should be negative, and let us call it minus K, say. Because force is restoring, since force F is restoring, we therefore get the final form of restoring force, and it is F equal to minus K for A1, so it will be minus Kx. So this is the form of restoring force, and therefore it is called linear because F is proportional to x to the power 1. So it is linear. Negative means it is restoring, and this is a force. The motion of the particle therefore occurs under a linear restoring force if x is small or the amplitude is small, and this motion is of simple nature, and that is why we have simple harmonic motion. So simple because of this fact. Now, why harmonic? We'll discuss that in details in a separate video, but the answer is that this particle satisfies a differential equation which, when solved, gives us terms like sine and cosine. So the movement of the particle with time is sinusoidal or cosinusoidal, and sine, omega t, cos omega t terms are called harmonic terms. So in other words, if displacement of the particle is small from the equilibrium position, then the particle will execute a motion over time which can be described by harmonic terms, and also over a linear path. So the motion is simple, the motion is harmonic. We will now write down the definition of simple harmonic motion. So definition of simple harmonic motion. Small amplitude motion of a system that occurs under a linear restoring force is called simple harmonic motion. And the salient features are, or the important features are, SHM is caused by a linear restoring force and that is F equal to minus Kx. Second point is path of linear harmonic oscillator is linear, as the name implies. This is called linear harmonic oscillator or simple harmonic oscillator. It is a small amplitude motion. With angular restriction of 4 degree with respect to the equilibrium position. Another point is that the motion is simple harmonic with respect to time. And what does this mean? This means the displacement, the velocity, the acceleration all vary as sin omega t or cosine omega t. Also, the motion is simple since the amplitude does not decay. The amplitude is constant with time because energy is conserved. Energy is constant, and these things will be discussed in separate video. Let us note that F equal to minus kx is a very important law which is also called Hooke's law. For 1D case, attaching the vector sign, because force is a vector, we can write it in this way. And this is the equilibrium position. This is the instantaneous position of the particle x at time t, and this is x hat. This equilibrium position is taken as the origin, and this particle is a linear harmonic oscillator. So it is written as LHO. For 3D case, we'll have two more terms like that, and we'll have kx x hat plus y hat plus z hat, and that gives rise to this expression, which can also be written as r hat. Let us now make a plot of the linear restoring force against displacement. In reality, let us plot either minus f or mod f versus x, because f is minus kx. So let us ignore this negative sign and plot it as follows. So this is x-axis, the abscissa, and this is called the ordinate, where we will plot modulus of f. Now clearly minus f is kx, or equivalently mod f is kx. So the plot should be linear. So the plot is of this type. But we have to be careful about the restriction on x. So this is linear under a certain approximation, and the approximation is that x is small, under which the motion is simple harmonic, which is also called the elastic limit. So the force varies as x linearly if x is small. And this region is called the Hooke's region. Within elastic limit. Only in this region f is proportional to x and small amplitude vibration occurs. Which is a simple harmonic movement. So this is x equal to small region. Beyond this region, that is for large x. So in this region, where x is large, in this region, where x is large, f is nonlinear. Because along with the linear part, there will be presence of quadratic part, cubic part, and so on and so forth. So in this region, there will be distortion, say of this type, and in this region also there will be distortion. The car will bend from its linear movement. So there will be distortion. So let me reiterate that this region is linear. Here f is proportional to x, but outside it f is not proportional to x and the dependence is extremely complicated, and this is called distortion. The Hooke's law is f equal to minus kx. Now what is the value of k? So let us make a note on k. It follows from here that k is minus f by x, and this is linear restoring force. So linear restoring, and hence the negative sign, force per unit displacement. We can also write it as mod f by x, and this k is called spring constant. It is also called stiffness constant. Now what is its unit? The unit of force is Newton and the unit of displacement is meter. So it is Newton per meter. What is the significance of k? To study significance of k, again we have to look at this relation. So let us rewrite it. So k is f by x. Now if x is 1 or unity, then k is the linear restoring force. Now spring constant or stiffness constant is a property of the system, just like mass, charge, etc. Clear that if a system has large k, then to produce unit displacement, the amount of applied force should be large. And this is because the system tries to retain its individuality. system tries to oppose our attempt to deform it. In other words, system is more elastic. So K large means elasticity of the system is large. On the other hand, if K is small for a system, this means that to produce unit displacement, we require a small amount of applied force. This means that the system very easily listens to us, so it fails to retain its individual characteristics. This means the system is less elastic. So K small means system is less elastic. Let us write all these things. K large means large F, and this F is the restoring force which is equal to the applied force. This means large applied force is needed to deform system or displace system, disturb the system by an amount of x equal to unity. System is more elastic as it tries to retain its individuality or characteristics. So it is not easily deformed. System is not easily deformed. It doesn't listen to us easily. We have to make it listen. Again, K small means low mod f. To deform the system by the same amount, say x equal to unity, we need a small force. Since system listens to us easily, so system does not retain its characteristics. Even under a small force, so it is easily deformed. So let us make a gist. K large means more elastic and K small means less elastic. So this is the significance of the spring constant or stiff constant. Put in a different way, K is a measure of how stiff, how much flexible, or how much elastic a system is.